Good day, students. So today we're going to talk about intensifying screens. Intensifying screen is a special and important accessory that is used for conventional radiography. Together with the X-ray film, this imaging is called film screen imaging or film screen system. The introduction of intensifying screen to the field of radiologic technology, I believe, is one of the most important discovery following the discovery of X-rays, and it has probably allowed the progress of the application of X-ray in medical field. I will talk about this more later in our discussion. So what are the learning objectives of this particular topic? So at the end of the topic, I expect you to be able to describe the role of intensifying screen in the production of image and the reduction of dose, to know the different parts of the intensifying screen, to describe the characteristics of intensifying screen and how it affects the quality of the image produced and the dose of patient. And last, to differentiate the two types of intensifying screen. So let us first define what intensifying screen is. Intensifying screen is a device that converts X-rays to visible light. It is probably hard to believe that a very powerful and energetic beam of X-ray can be converted to just an ordinary visible light. However, as radiologic technology students, you probably already know that it can be done because both energy belongs to the same electromagnetic spectrum. The intensifying screen only converts a higher energy electromagnetic radiation to a lower energy electromagnetic radiation. So it doesn't change the kind of energy it is, but rather it only changes the energy from a higher energy X-rays to just a lower energy or a lower form of electromagnetic radiation, which is the visible light. Now, when X-rays were converted to light photons, the high energy X-ray was converted to thousands of light photons. Why? Because we have to conserve energy. And because X-rays are very energetic, that one X-ray photon is now converted to thousands of light photons. The sum total of all the energy of the light photons that is emitted in response to that exposure should be almost equivalent to the amount of energy of that X-ray photon. In effect, films are exposed to many photons as a result of this conversion. And that is precisely the reason why this is called intensifying screen. What it intensifies, it is the number of photons that will interact with the X-ray film. In converting X-rays to visible light, we also allow the film to be exposed to the wavelength of the visible spectrum that the film is most sensitive. You have to remember that our film, although it is sensitive to gamma rays, X-rays, ultraviolet rays, but it is most sensitive to visible light. In particular, the blue and the green region of the visible spectrum, or we can say the blue and the green light. And so, by converting X-rays to visible light, we are allowing our X-ray film to be exposed to its most sensitive wavelength. Now, in general, films that are exposed using screens has an image that is produced 95% by light and only around 5% by X-rays. When you see a radiograph such as this chest X-ray, you have to think that the image that you see is caused by 95% light emitted from the intensifying screen and only around 5% by direct exposure to X-rays. So intensifying screens are designed to be mounted in pairs inside the cassette. A cassette, which is this one, is a device that holds our X-ray film. You have to remember that our X-ray film is sensitive to white light, and so we need a housing for us to be able to bring our X-ray film outside of the dark room. Now, the pairs of intensifying screens are actually mounted inside the cassette. So the white object here that you see are the pairs of intensifying screens. Now they are mounted both on the front part of the cassette and the back part of the cassette. So it might look like an ordinary cardboard, but believe me, this is a very, very special device. When the cassette is closed, the X-ray film is sandwiched tightly between two intensifying screens. We have here the intensifying screen 1 and another intensifying screen here. Now you might wonder, why do we have to use two intensifying screens? We are using two intensifying screen because you have to remember that our X-ray film is duplicitized or double coated. There are two emulsion layers coated on both sides of the film base, and there is a corresponding intensifying screen for each emulsion layer. When exposure is done, an X-ray photon will interact with the first intensifying screen and is absorbed by the phosphor crystal. In response, the phosphor crystal will emit light isotropically and will expose our X-ray film here. The same is true, there are also X-ray photons that will pass through the first intensifying screen without any effect and will be absorbed by the X-ray film itself. But there are also photons that will pass through the first intensifying screen and pass through the X-ray film and interact with the second intensifying screen and again absorbed by the phosphor crystals. Now, the X-ray photon that is absorbed by that phosphor crystal will again be converted to light photon, and that light photon will expose this emulsion layer here. Let us now talk about the advantages of using an intensifying screen. The intensifying screen reduces the exposure dose required for a particular examination. Remember that the intensifying screen converts one X-ray photon to thousands of light photons, therefore intensifying the number of photons that interacts with the X-ray film. Thus, we no longer need a very high amount of exposure in order to produce the necessary amount of density in our X-ray film or to produce the necessary image on our radiograph. The reduction in dose brought about the following advantages. First, it results to low patient dose. This is the primary advantage of using an intensifying screen. As I have mentioned in my introduction, intensifying screen is probably one of the most important discovery following the discovery of X-ray. Shortly after the discovery of X-ray, they have already recognized its importance in medical application. However, they have also acknowledged that it is harmful because of numerous reports of effects of the X-ray exposure. And in any medical application, we have to weigh the benefit versus the risk in doing a procedure. Fortunately, the use of intensifying screen has tremendously reduced the amount of exposure and therefore the dose to the patient, which makes the benefit of the application far outweighs the risk involved. Because of that, the application of X-ray to medical field has been accepted and has progressed to what we now have. Because of the reduced exposure, it makes it possible to make the time of exposure short, allowing imaging of the most body structures. The fast exposure time also leads to less motion and sharpness. Motion and sharpness leads to blurring of images. With the short exposure time that we use, there is lesser probability that motion will be caught on the radiograph. Finally, the reduced exposure also results to less thermal stress on the X-ray tube and reduced shielding requirement. The higher the speed of intensifying screen, the more pronounced these advantages are. However, the intensifying screen also comes with a disadvantage in that it introduces the screen and sharpness, resulting to low detail image or poor resolution images. When film is directly exposed to X-ray, the short wavelength X-ray only exposes a very small portion of the film. resulting to a very fine image detail. When intensifying screen were used, the single X-ray photon interacts with the phosphor crystal of the intensifying screen and was converted to many light photons that are emitted isotropically. That is, in all directions, not just towards the film, but those light photons that allowed to interact with the X-ray film will affect a large area of the film compared to a direct exposure film. This large area of exposure results from light emitted by the intensifying screen is called the screen unsharpness. Now let us discuss the construction of the intensifying screen. Shown here is the cross-sectional structure of the intensifying screen. The layer that's closest to the X-ray film is the supercoat. Next to it is the active phosphor layer, and then a thin coat of substratum or adhesive layer. Beneath the substratum is the reflective layer, followed by the base material. If an intensifying screen has an absorptive layer instead of a reflective layer, the reflective layer is just incorporated into the base material. Some modern intensifying screen also incorporates the reflective layer to base material. The base material is the layer that is attached to the cassette. The layer that is closest to the film is the supercoat. It is the protective layer of the intensifying screen. According to Bushong, the usual thickness is about 10 to 20 microns thick, but some other books says that it is much thinner at 8 micron thick. It is made of cellulose acetobutyrate or other polymer. Supercoat serves three functions. First, it protects the delicate phosphor layer from mechanical damage because it is constantly rubbed with fingers and film during loading and unloading of film. It also provides a surface which can be cleaned without damaging the phosphor layer, and provides a smooth evacuation of entrapped air, resulting in a good film screen contact. Supercoat should also be a poor conductor of static electricity, since films are constantly rubbed on its surface. Static electricity causes static artifacts to be developed on the film. The surface is also made of varying roughness and smoothness. Smooth to facilitate evacuation of air, yet rough to hold the film in place when opened. Behind the supercoat is the phosphor layer. It is the most important part and active layer of the intensifying screen. It is made from a dispersion of phosphor crystals within a suitable binder. The usual thickness of the phosphor layer is around 150 micrometer, but can reach the thickness of up to 300 micrometer thick. The binder used for phosphor layer is an acetate acrylate. The characteristics of acetate acrylate includes the following. First, it should be inert to phosphor crystals and the light they emit, which means that it should not discolor or change in form when exposed to the light emitted by the phosphor crystals. It should also be flexible to allow even and known dispersion of the phosphor in the binder and to allow the phosphor layer to be coated onto the base at the required thickness. The last two ensures that the light emission is uniform throughout the intensifying screen. The other component of the phosphor layer is the phosphor crystal. It is a metallic crystalline solid, can be naturally occurring or artificially made, and exhibits the property of fluorescence when exposed to X-rays, and can also be manufactured in useful form to produce high image quality. There are two types of phosphor crystals used for X-ray imaging, the calcium tungstate and the rare earth screen. We are going to discuss the two types in detail in succeeding slides. As we have mentioned, phosphor crystals exhibit the property of fluorescence. Fluorescence is a property that belongs to a more general term called luminescence. Luminescence is the ability of some materials to emit light in response to some outside stimulation. Stimulants can be electricity, or light energy, or radiant energy, and the like. There are two types of luminescence: the phosphorescence and the fluorescence. Phosphorescence is the ability of a material to continuously emit light even after stimulation. Other, more popular term for phosphorescence is afterglow. Fluorescence, on the other hand, is the ability of material to emit light only during stimulation. When the stimulant ceases, the emission of light ceases. Phosphor crystals of intensifying screen exhibits fluorescence. In fact, continuous emission of light for intensifying screen after stimulation is undesirable, as this will cause poor detail images. The next layer is the substratum. Substratum, or adhesive layer, attaches the phosphor layer to the base material. It should be as thin as possible, but should provide adequate adhesion between the phosphor and the base material. The next layer can either be a reflective layer or absorptive layer. They have opposite effect on the characteristic of the intensifying screen and are chosen depending on the IS intended use. Modern technology has already incorporated the reflective or absorptive layer in the upper part of the base instead of a separate layer. Reflective layer intercepts light going away from the film and redirects it towards the film. When X-ray photons interacts with the phosphor crystal, it will be absorbed, and in return, the phosphor crystal will emit light in all directions. There are some light photons that will be emitted towards the X-ray film, but there are also some light photons that will be emitted that is traveling away from the X-ray film. The reflective layer here will intercept those light that is traveling away from the X-ray film and redirects it back towards the X-ray film. Therefore, the reflective layer effectively increases the number of light photons that will interact with the X-ray film, increasing the efficiency of the intensifying screen, but will also widen the area of exposure that will result to greater degree of screen unsharpness. So again, reflective layer increases the speed, but increases also the amount of unsharpness. It is made from thin coating of titanium dioxide or any other similar shiny substances. On the other hand, absorptive layer absorbs the light traveling away from the film. It has an opposite effect compared to the reflective layer. When no absorptive or reflective layer was used on intensifying screen, there was always a small amount of those light that's traveling away from the film that will be reflected back due to the difference between the material that is used for the phosphor layer and the base material. The absorptive layer, which is made from dye, which is very good in absorbing light photons, make sure that no light that is traveling away from the film will be reflected back, resulting in good resolution image but poor speed intensifying screen. So again, the absorptive layer slows down the speed of the system but has the advantage of providing a sharper image. This layer is made of dye incorporated in the base material. The layer that is farthest from the film is the base material. It acts as a support for all other layers of the intensifying screen, especially the active phosphor layer. Cardboard was first used as base material but was replaced by polyester because of polyester's durability. The usual thickness of base is 1000 micrometer thick. Thin base was mostly used for intensifying screen mounted on the rapid film changer used for angiography when digital imaging is not yet introduced. The following are the characteristics of a good base material. It should be rugged and moisture resistant. It should be resistant to radiation damage and discoloration. It should be chemically inert and lacking impurities. Let us now discuss the different types of phosphors. There are two types of phosphors, calcium tungstate and rare earth phosphors. Calcium tungstate is a naturally occurring phosphor and produces a continuous spectrum, principally in the blue part of the visible spectrum, with the peak output at approximately 425 nanometers, which is very compatible with the sensitivity of our monochromatic film, which is also at around 430 nanometers. It was first discovered by Thomas Edison for fluoroscopic screen, but was later adapted for use with medical X-ray film by Michael Pupin. The other type of screen is the rare earth intensifying screen. Rare earths are soft, malleable metals that can be made to emit light upon stimulation by X-rays. These phosphors require an activator for them to emit light. It was first introduced by three scientists in the early 70s. Shown here is the spectral sensitivity of the orthochromatic film and the spectral emission of the gadolinium oxysulfide intensifying screen. As you can see, the peak sensitivity of our orthochromatic film is located at around 550 nanometers, and it is very compatible with the peak emission of our gadolinium oxysulfide intensifying screen, which has a peak emission at around 550 nanometer also. Aside from the gadolinium oxysulfide rare earth screens, other rare earth phosphors were also introduced. So this includes the lanthanum oxybromide with terbium activator, which emits light principally in the blue region of the visible spectrum. The other one is the barium fluorochloride, this time with the europium activator, but this emits wavelength in the ultraviolet radiation. Now, performance of the intensifying screens can be measured using a number of different measures. First is the conversion efficiency. It is the efficiency with which the phosphorus converts X-rays to visible light. It is actually the ability of the intensifying screen to absorb X-rays, to convert it to light, and to allow the light to escape from the screen and expose the film. So shown here is actually the formula to compute for efficiency. Now, as you can see, there are three factors that affects efficiency. First is the absorption. This is talking about the absorption of X-ray photons by the phosphor crystals. So factors such as how big the crystal is would affect the absorption ability of the intensifying screen or the phosphor crystal. Now, the next factor is the conversion. Now, after absorption, the phosphor crystals will need now to convert the X-ray photons to visible light. Now, the kind of phosphor crystal, whether it is a calcium tungstate or a rare earth intensifying screen, would therefore affect the conversion of the X-ray photons to visible light by the phosphor crystals. And then finally, there is this emission property. Now, the emission is affected by other factors such as the kind of material that is used as a binder, the supercoat, whether there is a reflective or absorptive layer, which affects how much amount of light photons will be allowed to escape the intensifying screen itself. So all of this combined is a measure of the conversion efficiency of the intensifying screen. Now, a typical conversion for rare earth intensifying screen is 1 is to 1000 light photons per incident of 50 kiloelectron volts X-ray photons. So that means to say that for every one X-ray photon that our intensifying screen receives at an energy of around 50 kiloelectron volts, it will emit in response to that around 1000 light photons. Now you have to take note that we are using higher energy X-ray photons than this 50 kilo electron volt. Therefore, one X-ray photon can be converted to much more than 1,000 light photons. Another measure of the intensifying action of the screen is actually the screen speed. Now, screen speed is a relative number that describes how efficiently X-rays are converted to light. Screen speed gives us a numerical value for efficiency that is much easier to understand. Shown here is the typical screen speed of the calcium tungstate intensifying screen here. And in comparison to that, the speed of the rare earth intensifying screen, particularly that of the gadolinium oxysulfide screen. Notice that the highest screen speed for the calcium tungstate is 250. They can no longer manufacture screens with higher speed because it will produce already a poor detail image. On the other hand, manufacturers release gadolinium oxysulfide with higher screen speed up to around 1,600 screen speed without sacrificing detail. However, the use of too high speed and therefore very low exposure factor results to high noise due to quantum model. Therefore, the most common speed of the gadolinium oxysulfide is around 400 speed. Now, another one is the intensification factor. Intensification factor is the ratio of the X-ray exposure needed to produce the same density on the film with and without the screen. Intensification factor can be computed using this formula. Intensification factor is equal to exposure required to produce net density 1 without screens divided by the exposure required to produce net density 1 with screens. So practically what you are doing here is to compare the two exposure factors, one when you have taken a particular image without intensifying screen, and the other one when you use the intensifying screen. Now, it tells us how much reduction in dose is required for a particular intensifying screen. An intensification factor of 2 means that exposure factor needs to be reduced by 1/2 if the intensifying screen will be used. The higher the intensification factor, the higher will be the reduction in the amount of exposure required for each examination. Now let us discuss more about the screen speed and its relationship to detail. The relationship between screen speed and detail is a reciprocal one. As the speed of the intensifying screen increases, the amount of detail decreases. There are several factors affecting speed. Some also affects detail, but not all. The first is the phosphor grain size. The bigger the average grain size, the more light it will emit, but the greater the divergence of the light emitted, hence the poor detail. So as you can see from this illustration, one with a smaller grain size and one with a bigger grain size. The bigger grain size grain is more effective in absorbing X-ray photon and therefore will result to a higher speed, but it also emits a more divergent light pattern that affects a greater portion of the X-ray film here in comparison to the one with the smaller grain size. And so, as we have mentioned, a bigger grain size would result to a higher speed intensifying screen, but will also result to a poor detail image. Next is the thickness of the phosphor layer. The thicker the phosphor layer, the more crystal it contains, and therefore the more light emitted. However, the further crystal will emit more divergent light, hence the poor detail. So this is also shown in this illustration. As you can see, we have an intensifying screen with a thin phosphor layer and another intensifying screen with a thick phosphor layer. Now, the divergence of light that is emitted by this phosphor crystal that is located at the middle of the phosphor layer will affect this portion of the X-ray film here. On the other hand, this particular crystal that's located at the middle of a thicker phosphor layer will emit a more divergent light because of the distance from the film and affects a bigger portion of the X-ray film. Because there are more crystal that's present in this thicker layer, there will be more light emitted, but each crystal will also affect a bigger portion of the film and therefore result to a poor detail image. Another factor is the presence of reflective or absorptive layer. As we have already discussed earlier, reflective layer produces high screen speed but poor detail, while absorptive layer produces low speed screen but good detail. Screens are also dependent on the technical factor used, particularly the KBP. IS, especially the rare earth intensifying screen, exhibits its highest response only when exposed to KBP between 80 to 85. The IS will exhibit a lower speed when exposed to either lower or higher factor than is recommended. However, in doing radiographic examinations, it is the thickness of the part under study that will determine the KBP that we use for every particular examination. There are also factors that affect speed but not detail. Coating weight increases speed but not detail. Coating weight is the number of phosphor crystals that is contained within the phosphor layer. The more phosphor crystals it contains, the higher would be the coating weight. A higher coating weight will definitely emit more light photons that is attributed to the increased speed of the intensifying screen. Now, another factor is the phosphor type. Rare earth has higher speed than calcium tungstate, as we have already discussed in screen speed, but doesn't mean that rare earth will produce a poor detail. In fact, the gadolinium oxysulfide intensifying screen still produces a more detailed image than the calcium tungstate. The introduction of intensifying screen has resulted to poor detail images. Factors that may affect detail are the following. First is the screen and sharpness, which is due to the divergent emission of light coming from the intensifying screen, which we have already discussed in detail. The next is the crossover, which is the result of the use of two intensifying screens with two layers of emulsion. The widening light beam emitted by the crystal causes a shadowy, less sharp image in the emulsion layer furthest from the intensifying screen as it passes from one emulsion to another. The difference between the sizes of the image recorded on the first emulsion and the size of the image on the second emulsion is the parallax error. The difference between the density that is recorded on the first emulsion and the density that is recorded on the second emulsion is the crossover. And since the density that is recorded on the second emulsion is lesser than the density that is recorded on the first emulsion, it becomes somewhat like a shadow, and this results to a poor detail image. Another one is the structure mottle, which is caused by the fact that it is not possible to evenly disperse the phosphor crystal throughout the binder medium. The clumping of the phosphor crystal causes this mottling on the X-ray film. These dots that comprises the image that you see on this radiograph is actually a mottle on the X-ray film. Now, this is further aggravated by the quantum mottle, which is caused by too few number of photons interacting with the film, primarily caused by the use of too low MAS factor. This has become possible because the intensifying screen allows us to use low exposure factors. The higher the speed of the intensifying screen, the lower the MAS required per examination and the greater the possibility of quantum mottle. Finally, is the film screen contact. Intensifying screen is designed to be directly in contact with the X-ray film. Poor film screen contact causes the light emitted by the intensifying screen to diffuse before it reaches the film, so that the image produced is unsharp. This illustration shows a portion where there is a poor film screen contact. This could be because of the air that is entrapped inside the cassette or a dirt in the intensifying screen. As you can see, the intensifying screen is now much farther from the X-ray film. The light that is emitted by the phosphor crystal will be more divergent before they interact with the X-ray film, and this widening light beam causes the poor detail on the image. This ends our presentation for today. Thank you for listening.